All right. Now we're going to go, we've looked at the shapes. We're going to do Unit 9. Unit 9 is now, how do we interpret the graphs? What do we do with the information that the graph can tell us, and how do we get that information? So first, here we go. It says to me that the following displacement time graph describes the movement of a car going on a straight line, which is the only way we do this, in an easterly direction. So now look at here. Because this is going to the top, what this is telling me is that east is positive. Okay? So every time we have a displacement above the graph, it's going easterly. Anything below the graph is west. Okay? So this part of the motion is west. Now they ask, which sections of this graph illustrate, number 1, movement eastwards? Well, I just said to you it's everything above the graph, so it's A to B. The gradient is positive. Is the car moving from B to C? No. It stopped. The velocity isn't changing. Sorry, the displacement isn't changing. But also what we should have put here is, no, I'm lying to you. This here, it's going from 50 meters away, getting to 0. This is still not east. It's turned around. What this graph is telling me is it went for 50 meters, stopped, then went back to the starting point, and then went past the starting point, okay? Movement westwards towards the starting point. That's the second part. So that's C to D. The gradient is negative. Where's it at rest? Well, we just said there, from B to C. Here, displacement didn't change. Now, this should say negative velocity, okay, because I can't get acceleration off a displacement time graph. So this here is my negative velocity because it's got a negative gradient. When I'm finding that gradient, I get a negative value. The gradient gives me velocity. So that's from C to E. What is the total distance covered by the car? Well, from A to B it went 50 meters. You need to have your graph in front of you while I do this. From B to C it was at rest. Then from C to D it went 50 again. Distance means I don't care about direction. From D to E it then went another 50 meters. So my total distance is just adding all three together. Alright, because it went east, then it went west, then it went west again. Now they want the car's displacement. Now the positive and negative is important. Okay, so now we're going to go plus 50 from A to B, 0 from B to C, then it changed direction. So it went minus 50 from C to D and minus 50 from D to E. It's minus 50. Minus 50 means that it's at 50 meters west. Again, remember what I said to you. 50 meters east. Then it went 50 meters west to get to its starting point. And then we went 50 meters beyond that, which was west. They want the car's velocity in reverse gear. So reverse gear would be when it's going west. So if we look at our graph, we're going to look at the gradient. So remember, our graph does this. I need that gradient. Minus 50. Final displacement, there was minus 50. Initial, there was 50. Minus 50, minus 50. This was at 10 seconds. This was at 18. Minus 12 and a half. So that means it was 12 and a half meters per second west. Okay. Oh, what's the car's velocity at D? Well, remember this. This is quite important. This is from C to D, D to E. I know D is where it cuts the x-axis, but it's going at constant velocity. So at any point along that line, the velocity is 12.5 meters per second. Don't even have to think about it. They want the velocity of the car during intervals AB and BC, and then they want a velocity time graph. Remember, and you'd have to work this out. So AB, and I'm going to leave this to you, is this point. Okay. So it's the time it takes to carry that, and you're going to work out the gradient. Then we recognize that from B to C, it's stationary. So the velocity is naught. So look what happens. This is from, oopsie, let's go back. This is A to B, B to C, C to F. Constant velocity, it's not changing, so they straight lines. Second example. Now we've got a velocity time graph. Now because this velocity is at an angle, that means there's acceleration. There's no acceleration, it hasn't stopped. It's going at 60 meters per second. Then it's slowing down, changing direction, and slowing down in the opposite direction again. It's initially going east, so this is positive and that's going to the east. This is also a positive gradient, so it's going east, minus, and minus. So at A to B, C to D, D to E, E to, oopsie, A to B, D to E to F, it's got a positive acceleration, okay? C to E, it's got a negative acceleration. Which part of the graphs indicate the following? Well, B to C, remember your graph did this. B to C is the flat part, constant velocity. Movement eastward, we just spoke about that. It's when we have a positive gradient and a positive gradient. So it's A to D. Oh, no, hang on, wait. Sorry, I need to read the question properly. It says movement eastwards. All of this is they're going to the east, okay? Because it's above the line. All of this is it's moving west, okay? Movement westwards, when's it going backwards? Well, from D to F, essentially what's happened is this. From A to B, it's speeding up in the forward direction. Then it's going to constant velocity in the forward direction. Then it's slowing down, okay? Once it slows down enough, it changes direction and speeds up for a little bit and then slows down in the opposite direction. So this is A to B to C to D to E to F, okay? Acceleration to the east. Now this is when we have the positive gradient. So it's A to B and E to F. Acceleration to the west, it's where we have a negative gradient. So it's C to E. It's all of that because it's in the negative direction. Ooh, a position of rest. So when we go back to our graph, remember it does this. Velocity has to be 0 for a position of rest. That means it's only at A, D, and F. Because A is 0, F is 0. Okay? Point furthest from the origin. Let's look at my diagram, which is getting more and more messy as we go along. Sorry about that. So if we go back here, remember, this is all in the same direction. This is where it turns around. Okay, so what is the question? The point furthest from the origin. So if we go back here, it's point D, because it was still moving away from the beginning. So that makes it D. There we go. Determine the acceleration for each of the following sections. Now, I really need you to have your graph in front of you, because you know I don't have mine here. So it's that, and that. All right. So from A to B, B to C, C to E, it's every point. So we're going to look at the gradient from A to B. It's 60 minus 0. Please don't leave out the minuses. The minus 0, very important. So it's 20 meters per second squared east. The gradient of a velocity time graph gives me acceleration. From B to C, it's 0 because it didn't speed up or slow down. From C to E, now watch. We get negative 30, which is what we expected because we know it's got a negative gradient. That means it's going 30 meters per second squared west. Then from E to F, it's positive gradient again. So it's minus 60. So it's 20 meters per second squared east. We did change acceleration, so it's not constant acceleration, but it changes at very specific points. It's not continually changing. Okay? Then they say use the graph and determine the displacement of the trolley. Now I've gone and drawn the graph again because this is quite important. We have to look at the area under the graph. And displacement means I've got to take this negative into account. I'm going to break this up into a whole bunch of little parts. Part 1, which is a triangle. Then I'm going to do number 2, which is a rectangle. Then we've got 3, which is another triangle. Oopsie. And then I've got 4 over here, which is another triangle. Okay? If you can remember the area of a rhombus, go ahead and do it. And you can do 1, 2, and 3 all in one go. But rather just break it up into different triangles. So, the area under the graph is area 1 plus area 2 plus area 3 plus area 4. Area 1 is a triangle, half base times height. Area 2 is length times breadth, half base times height, half base times height. Watch what's important about displacement. This height is positive. Okay, so the time is always positive because it's on the time axis. You know this. This is minus 60 because it's minus 60 here. Displacement needs direction. So we get 60 meters east. We get a positive displacement. So basically my car went 90 meters, then 60 meters, then 60 meters, turned around and went another 150 meters backwards. Okay? Now they want the total distance. This is the difference. Still using all 4 areas. But now, I don't worry about the minus. I ignore the minus. So that's 60. That means totally they went 360 meters. But from the starting point, they'd only gone 150. Now they want the average velocity for the trolley in 11 seconds. Remember, average velocity means total displacement over total time. Okay? We're not using distance. We'd use distance for speed. So we're looking at average. Okay, and remember over there, you don't have to write it out like that. Instead, over here, oopsie. Alrighty, it doesn't want to go away. We could have written V with a minus line over it, okay? So it's 5,45 meters per second east. It's a vector. Now they want average speed. Average speed means I need the distance. The distance we worked out to be 360. So average speed, 360 divided by 11, 32. Significantly higher because distance doesn't take direction into account. Then they want the magnitude of the trolley's acceleration at 8 seconds. Well, you've worked that out when you did the acceleration at different points. So you need to go back to the graph and see where those 8 seconds are. That gives you the magnitude. That means I don't need direction. Then they want what is the trolley's instantaneous acceleration at 1.5 seconds. You will have worked out the gradient of the graph at 1.5 for the whole section, no matter where it falls in. So that's 20 meters per second east. Magnitude over here means I don't need direction. Here they didn't say magnitude only, so I have to put direction. Now, you need to make sure you can do activity 1 on page 239 before you move on. Okay. Oh, no, we're not there yet. Let's